Hi there, in this video I'm going to be proving the definition for the inverse hyperbolic function cos. Okay, so let me prove the definition for inverse hyperbolic cos for you. So if you looked at the previous video, it follows the same method as the proof for the inverse hyperbolic sine function. So let's go through this definition. So result number 2. So I hope you can see that. So let me underline that. So the inverse hyperbolic cos definition is ln x plus the square root of x squared minus 1. Okay, so that result is true for values of x greater than or equal to 1. So as I said, it follows the same method as the previous proof for the inverse hyperbolic sine function. So here's the proof. Let's underline this. So step number 1, I let y equal the inverse hyperbolic cos x. Okay, so if you looked at the previous video, that is exactly what I did for the inverse hyperbolic sine definition proof. So let y equal the inverse hyperbolic cos function in this case. Okay, and if we rewrite this, we can rewrite this as hyperbolic cos y equals x. Okay, so that is step number 1. In step number 2, I'm going to use a definition of the hyperbolic cos function and find an expression for hyperbolic cos y. So remember the definition for hyperbolic cos, it's e to the x plus e to the minus x divided by 2, which means hyperbolic cos y is e to the y plus e to the minus y divided by 2, which is equal to x in this case. Now, if I cross multiply, I'm going to have e to the y plus e to the minus y equaling 2x on the right hand side. Okay, and like with the previous proof that we've seen in the previous video, I don't like negative powers, so I'm going to get rid of this negative power by multiplying by e to the y throughout. So if I multiply throughout by e to the y, we're going to have e to the 2y plus 1. So remember, e to the y times e to the minus y is e to the 0, which is equal to 1. And that's equal to 2x e to the y. Okay, so I'm going to move all of my terms to one side. So for me, I'm going to move this term to the left hand side to give me e to the 2y minus 2x e to the y plus 1 is equal to 0. Okay, and if you note in the previous video, we could make this equation resemble a quadratic as e to the 2y. Okay, so if we looked at the previous proof, e to the 2y, okay, is the same as e to the y squared using this result in indices. Okay, so let's use that result over here. So e to the 2y is e to the power y squared minus 2x e to the y plus 1 is equal to 0. Okay, so that takes us to step number 3, because I'm going to make this resemble a quadratic by replacing the e to the y terms by a letter. So I tend to use t. So let me let t equal e to the y. So if I let t equal e to the y, the equation will become t squared minus 2xt plus 1 is equal to 0. And from this point, we're going to use our quadratic formula. Okay, so let's use the quadratic formula. So using t is equal to minus b plus or minus square root b squared minus 4ac divided by 2a. So take a ruler and underline that. So in this quadratic formula, the a term being the coefficient of t squared is 1, b is minus 2x, coefficient of t, c is plus 1. So a is 1, b is minus 2x, c is 1. So if I substitute those terms into the formula, we're going to have t is equal to minus b, which is minus 2x, plus or minus square root so I hope you can see that. So b squared, b is minus 2x, so minus 2x squared, okay, minus 4 into a being 1, c being 1 also, divided by 2 into a being 1. Okay, so let me continue on the next page. So t will then be, so if I expand these brackets, so minus into minus 2x is plus 2x, so 2x plus or minus square root. So minus 2x squared equates to 4x squared, and minus 4 times 1 times 1 is minus 4. So we're going to have 4x squared minus 4 under the root. So let's make a note. So 4x squared minus 4 under the square root, divided by, and if we go back to the last page, 2 into 1 in the denominator is 2. So let's make a note. So divided by 2. Okay. Now, if you've seen the previous video, what I did was I've extracted a common factor of 4, okay, under the root, and I've taken that common factor of 4 out of the root. So if you take the common factor of 4 out of your square root, that's going to end up with 2. Okay, so let me show you what I mean. So t will be 2x plus or minus. So taking that common factor of 4 out of the square root, so square root of 4 is a 2. And be careful, because you're going to be ending up with x squared minus 1 within the root, everything over 2. Okay, and what I'm going to do from here on is, let me take a common factor of 2 from the numerator. So if I take out a common factor of 2 from the numerator, we're going to end up with x plus or minus square root x squared minus 1, everything divided by 2. Okay, and from this point forward, these two 2's will cancel to give you t is equal to x plus or minus the square root of x squared minus 1. Okay, so that will take us to the last step, step number 4. So if we go back to the previous page, so remember t is e to the y, so let me replace the t by e to the y. So since t equals e to the y, that means e to the y will be x plus or minus square root x squared minus 1. Okay, so I'm going to take ln's on both sides, or you can take logs on both sides. So if I take ln's on both sides, discounting that negative sign, okay, so y will then be ln x plus square root x squared minus 1. And if we go back to the previous page, so remember, y is the inverse hyperbolic cos of x. So if we replace y by the inverse hyperbolic cos of x, you've got the definition or the result. Okay, so to conclude, hyperbolic cos inverse x is indeed ln x plus the square root of x squared minus 1. Okay, so that completes the proof. So that ends the video. I hope you found this video helpful. In the next video, I will be proving the result for the inverse hyperbolic tan function. Okay, so I hope to see you then.